Okay, so welcome to the second part of the video, and let me pull this once again in here. Okay, now, so as I told you last time, in the last video I thought we will do a 7 marker question in 7 minutes. See, what we have done is 2 plus 3 5, 5 plus 2 7, 7 plus 2 9. So 2 plus 2 4, 4 plus 3 7, 7 plus 2 9. Instead of 7 mark, we have completed 9 marks in 7 minutes. Okay, now let us continue with this one here. Now, so what was the question here? Let me just give a prelude of what we have done so far. So the question was that you have a spring. This spring was set to oscillation. There was a weight added over here, and then this was pulled down by a student to a distance of the displacement here was seen to be 0.04 meter. Then the value of K here is seen to be 18 Newton per meter. This is also given to you. And then what they did was they put this one inside a oil bath, and then they pulled it across and they asked question about what is happening over there. It's critically damped. This is what we have learned so far. Then a spring such as that in A is stretched horizontally, and a longitudinal wave is set up in the spring traveling to the right. Now instead of putting it like this, so you are going to put it like this over here. You are going to put it like this over here, and then you are going to create a longitudinal wave set up in the spring describing traveling to the right. What describe in terms of propagation of energy, what is meant by a longitudinal traveling wave? What do you mean by longitudinal traveling wave? Longitudinal wave is nothing but if the energy is going in this direction, then the particles also start vibrating like this. This is what we have seen in case of a sound wave. But you see in this question, they have asked something about a spring and they are asking longitudinal wave in this context. What you need to do? You need to describe it like this over here. So first what you do is you describe, because for 2 marks, describe about what is meant by a longitudinal wave. You say that the direction of a wave is parallel to the coil's deformation in the spring. This is the first thing that you say. This is the first thing that you say. And then you say the angle between the wave propagation and the spring vibration is 0 degrees. That's what you can say. Okay, 2 marks you can easily get this. In fact, this itself conveys this, but anyway, if you want to still elongate this one, you can write like this also here. Okay, or maybe you can put one more point about longitudinal wave. You can say that longitudinal wave requires matter, and without matter it will not be able to propagate. You can write that also. Okay, let us move on to the next question here. The graph shows how the displacement x of the coil of one coil C of the spring varies with time t. The speed of the wave is 3 centimeter per second. Okay, determine the wavelength of the wave. Determine the wavelength of the wave. Now x versus t is given. You need to find out the wavelength. Now what is given here? T is given, which means what? From here to here, the wavelength takes one time period. So you can easily say time period here is equal to 0.8 seconds. Then you can find out the frequency. Okay, before finding the frequency, you need wavelength, right? What we'll do is we write down the equation. V is equal to f lambda, right? Now f is nothing but 1 by t times lambda. What is that you need? You need lambda here. V is already given to you. Why do I need to find out the frequency? I can directly find lambda by the formula V into t, right? T goes that side, V into t. What is V here? 3 centimeter per second. 3 into 10 power minus 2 multiplied by t. What is t here? 0.8. So this should be 3 8s are 24. 2.4 into 10 to the power of minus 2 unit meters, or this should be equal to 2.4 centimeters, right? So 2.4 centimeters. Then draw on graph in C2 the displacement of a coil of the spring that is 1.8 centimeter away from C in the direction of traveling of the wave, explaining your answer. Okay, now displacement of a coil of the spring that is 1.8 centimeter away from C. What is 1.8 centimeter away from C? Okay, so you got the wavelength over here. Now you got 1.8 centimeter. See, when I say that the spring is something like 2.4 centimeter away from the point C, where is the point C here? Point C, x of displacement x of the coil C. So let us say this is your point C here. When I say take up a point which is 2.4 centimeter away from point C, 2.4 centimeters are one wavelength, right? Which means I would consider a point here. And if I say take out a point which is 2.4 divided by 2, which is 1.2 centimeter away from point C. Which point is this? This is your point C here. This will be the point over here. But what is being asked? He is not asking you 2.4 or 1.2, but he is asking 1.8 centimeter here. Where will 1.8 centimeter be? 1.8 centimeter would be somewhere in the middle. Why middle? Because 2.4 divided by 2 is 1.2. 1.2 divided by 2 is 0.6, right? 1.2 plus 0.6 is 1.8. Okay. So therefore 1.8 will be 3/4 of the wave. It will start from here. So now you depict the same wave like this, and then when this reaches a maximum, this will also reach a maximum like this. Then this will go like this over here, go like this over here, and then you go here, right? So this is the output for this, right? And then so we have explained this also. With this we come to an end to this particular problem. Thank you.